This is our class notes from 3.4, and we're using polynomial division to find the zeros or solutions to polynomial functions. These are the three types of solutions that we're looking for. Predominantly the techniques we're going to learn in this particular section are finding rational or real solutions to polynomial functions. But we need to be familiar with all three. We especially need to be familiar with any complex roots that we might find. Here are some examples of some complex solutions. We have to remember that if we find one of these, we've also found another one, because complex or imaginary roots always exist in conjugate pairs. Be careful and let you know what a conjugate is. It doesn't mean just merely change the sign. It means change the sign of the imaginary portion of the number. Okay, let's use long division to find the roots of this particular polynomial function. All right, it's too complex to factor, so we're going to try to factor it by dividing in a very simple binomial, x minus some constant c. But what do we use for c? The rational zero theorem will vastly narrow down all of our choices that we can use for c. The rational zero theorem looks at the lead coefficient of the original polynomial and the final constant term of the polynomial. We must be careful. This technique and all these different choices for c that it gives it are for real numbers only. It's not going to help us with those complex or imaginary roots. These are all of our possibilities from the rational zero theorem of possible values of x that will render the polynomial function zero. "16 numbers here is still a little bit too much for us to deal with. We could start guessing and checking and start dividing our polynomial by x minus 1, x plus 1, x minus 2, x plus 2, x plus 3, x minus 3, so on and so forth until we've exhausted all 16 possibilities. Let's make this easier. I see it in my graph. I have a touch and turn at x equal 2. That means I have a 0 of multiplicity of 2 at x equals 0. So that means x minus 2 and x minus 2 are two of my four possible solutions. Four possible solutions because this is a fourth order polynomial. X minus 2 is a known factor. So let's divide that into our original polynomial. It's no surprise that it divides in evenly with no remainder. And now we've reduced the complexity of our polynomial a little bit. But this quotient is still a little bit too difficult to factor. Let's take advantage of the fact that this has an even multiplicity. By dividing a second time, we'll reduce down to a nice, easy to manage quadratic. However, to finish factoring this, we're going to need to use the quadratic equation. All right, let's just do a little roadmap check and see where we're at so far. We know two of our roots, x equal 2, meaning if I plug x equal 2 into this polynomial, x equal positive 2, mind you, into this polynomial, it will render 0. Let's try to factor this and see if there's any quantities of x that will render this portion of the polynomial 0. Be careful how you use the quadratic formula and you simplify. All right, so this yields me two more answers. Negative 2 plus I root 2, negative 2 minus I root 2. Remember what we said about complex roots. Always in conjugate pairs. So now we have all four of our roots. There's the polynomial completely factored out. And these are all the values that will make the polynomial values of x, that will make the polynomial 0. Let's do checkpoint 5. Let's do our p's and q's. Use our lead coefficient and the constant of the polynomial. Okay, we're left with four possible numbers. Positive 1, positive 13, negative 13. We go to our graph and we see that it touches and turns at x equal 1. All right, so x equal 1 is the solution. If I plug in x equal 1 into my polynomial, it will render 0. That means x minus 1 is a factor. Let's divide by x minus 1 using synthetic division. Goes in evenly, no surprise there. We know this has an even multiplicity, so that means it occurs at least twice. So let's use it again. And again, it goes in evenly. And we're left over with x squared minus 4x plus 13. So where are we at so far? X minus 1 squared times this trinomial will equal 0. Let's look at this trinomial just like we did last time. Let's get our remaining factors. Again, not easily factorable. Let's use the quadratic formula. Be careful how we simplify. And there's our final two answers. So, our solutions are x minus 1, a multiplicity of 2 plus 3i, and x equal to minus 3i. You plug any of these values into our original function, it will yield 0. Let's look at problem number 25. We're working backwards. Here, they're giving me my zeros, and they are telling me that this is a degree of 3, which means it has 3 possible solutions. They only give me 2, but I know that imaginary solutions live in conjugate pairs. They also give me that if I put negative 1 into my final equation, it should yield negative 1 or 4. That's our remainder theorem. All right. There's my polynomial. There's 3 degrees. There's 3 possible solutions. So there's my polynomial factored out. Notice that I leave out this coefficient a. And we're going to solve for that. But first, we're going to FOIL together our factored polynomial. So there's the last 2 terms FOILed together. Now I'm going to FOIL together these 2 terms. But before I do this, I am going to evaluate my function at negative 1. The given information tells me that if I let x equal negative 1, then y should be negative 104. This allows me to substitute in and solve for my coefficient a. So here's my coefficient a is now 2. I'm going to do my last combination, my last foiling there, x minus 1 times x squared plus 25. In my last step, I'm going to distribute that too. All right, so that is indeed a third order polynomial, and if I factor it out, I'm going to find that my solutions are x equal positive 1, x is equal to positive 5i, and x is equal to negative 5i.